So thank you. First, let me thank the organizers for giving me this opportunity to present my work. So first I will explain what a branched projective structure is. So let me fix S a closed surface of genus G. Okay, so this is S. And first, a projective structure, not branched, on S. It is an atlas with values to CP1, and the changes of charts are Möbius transformation. So is an atlas UI-Fi, parameterized by the set I, such that Fi, it goes from UI to CP1, is a local homeomorphism. And on the intersections, on UI intersected Uj, Fi is Fj composed with a Gij, and Gij is an element of PSL2C, a projective transformation. Okay, so this is the Riemann sphere. And what it means is that any small open subset of S is identified to an open subset in CP1. So UI, Fi, and the identification is unique up to composition with the Möbius transformation. So on the intersection UI intersected Uj, Fi and Fj are the same up to composition with projective transformation. So this is a very old notion. It was introduced by Poincaré in the 1880s as an analogous of elliptic integrals for curves of genus greater than 2. And it was a tool, an important tool in the proof of the uniformization theorem. And so an important example of projective structure is given by the uniformization theorem. So it's the uniformizing projective structure. So X is a Riemann surface. And X tilde is its universal covering. So X tilde, it is either CP1, C, or the upper half plane H2, but in any case, it is contained in CP1. And the automorphisms of the universal covering are projective transformations. And as a consequence, you get a projective structure by taking local inverses of pi, of the universal covering. Are charts of a projective structure. Okay. Now there is another description of projective structure that is due to Riemann. And so a projective structure on X, it is given by an atlas or by a quadrupole X, P, F, and S. So X is a complex structure on S. P, it is a holomorphic CP1 bundle. On X. F is a connection on P, so a holomorphic foliation on P. That is transverse to the fibers. And S is a holomorphic section of P that is everywhere transverse to the foliation. So S, holomorphic section, say from X to P, section, everywhere transverse to F. Okay, so how do you see this equivalence? The structure X, it is given by the atlas UIFI. The changes of charts are holomorphic, so it's the atlas of a complex curve for Riemann surface. P, the CP1 bundle, it is given by the constant cocycle Gij. Okay, this relation implies that Gij is a cocycle, so it defines a CP1 bundle, and since it's constant, it defines a flat CP1 bundle. So CP1 bundle with holomorphic foliation. And S on each UI is given by Fi, which is a local biholomorphism. And so it implies that that the section is everywhere transverse to F. So this kind of thing, holomorphic CP1 bundle that with a connection and a section, it's quite a common object, say. Only the last condition is very restrictive. And so the idea is to study these objects without the last condition. And this is the notion of a branched projective structure. So, branched projective structure. I will write a BPS in my talk. So it is this quadruple where X, P, and F are so a flat holomorphic CP1 bundle, and S doesn't have to be everywhere transverse. It just has to be not a leaf of F. So it's not a flat section. And so there is also, you can also define such a structure with an atlas. So branched projective structure. Okay, BPS. And if you define it as an atlas, you allow the charts to have ramification points. You allow the Fi to be local, to be ramified coverings. Ramified coverings over their image. So that's the notion I'm going to talk about. Okay, so when you have a branch projective structure, then you have a branching divisor. Which is the tangency locus of the section and the foliation. Or you can also see it as the ramification points of the charts. And then, so there is also a branching degree, which is the degree of the branching divisor. So let me call D this divisor, and the branching degree is the degree of D. Okay. So a basic example of a branch projective structure is a ramified covering of the projective line. This is a branch projective structure where the associated flat CP1 bundle is the trivial flat CP1 bundle. Another example. So there are many cases where they appear, but one of them is, for instance, comes from Higgs bundles. So if I take a SL2R Higgs bundle, you can see it as a, so say X a Riemann surface, okay, on X. X is still a Riemann surface. So it is a couple L phi, where L is a holomorphic line bundle on X. And the Higgs field phi, it is a section of the cotangent bundle Kx tensorized with L2 plus L minus 2. This is an SL2R Higgs bundle. And so in 2014, Gayotto introduced the notion of the conformal limit of L phi, which is a holomorphic connection, so a particular holomorphic connection on an extension of L by L dual. So a holomorphic connection nabla on some extension of L by L dual. And so if you call P the quadruple X P of E, which is the projectivized bundle of associated to E, F nabla, which is the foliation induced by the connection nabla, and P of L. So this is the foliation induced, foliation and P of E induced by nabla. by the connection. And you suppose, for instance, it is enough to suppose that the degree of L is different of 0. Then L is not preserved by the connection, and so P of L is not a leaf of F nabla, and so P is a branch projective structure. So this is a context where branch projective structure appear. Okay, so I'm done about with the introduction, and what I'm interested in is the moduli space of these structures. So Pn of S, it is the space of marked branch projective structures on S of branching degree n. Quotiented by isomorphisms. So the fact I take marked branch projective structures means that I quotient only by isomorphisms that are, whose underlying diffeomorphism of S is isotopic to the identity. And so on Pn of S, we can define two forgetful maps. The first one goes to the Teichmuller space. T of S. So this is the space of marked complex structures. On S, so I write it Teich n, and to a branch projective structure, XPFS, it remembers only the Riemann surface X. And then there is another one to the space of flat bundles that I call R of S. So flat CP1 bundles on S. So this is a topological, purely topological object over isomorphisms. This is also the space of representations of the fundamental group of S to PSL2C, quotiented by PSL2C that act by conjugation. And then, so for this one, I call it hol n for holonomy, and I remember only the CP1 bundle with the foliation. Okay, so now from now on, I will suppose that the genus of S is at least 2. So in this case, recall that T of S is a complex manifold. of dimension 3G minus 3. And R of S, as a topological space, it is not separated, but it contains a nice dense open subset, R0 of S, that is a complex manifold and the dimension is 6G minus 6. And so in the unbranched case, so in the unbranched case, these two maps are very particular, and it's a very classical result. So unbranched case, when the branching degree is 0. So for projective structure, not branched. The first point, it is classical, but there is an important result of Bers in 1960 that led to it. It is that P0 of S, it is a complex manifold of dimension 6G minus 6. The second point is about the map to the Teichmuller space. So if I take X in the Teichmuller space, the fiber over X, the fiber of Teich 0 over X is very nice. It is an affine space. Directed by the space of global holomorphic quadratic differentials. And the last point, and this is, so again, this is very classical, but it was written in modern terms by Gunning. And the last point is about the holonomy. And this is a result by Heschal and Hubbard. So the holonomy map, hol n, it takes values in the nice open set R0 in the complex manifold R0 of S, and it is a local biallomorphism. Takes values in a local biallomorphism. So the very nice behavior of these of the Teichmuller map and the holonomy map are an important reason why people are interested in projective structures. And so the question is what happens when we remove this restrictive condition on the section S, and we look at branched projective structures. So the question is the branched case. So there were results in that sense, in particular Mandelbaum in 1972. So Mandelbaum is the one who introduced the definition of a branched projective structure. So the first question he asks is, what about the moduli space? And what he found is that if I fix a complex structure and D a divisor on X, then the space, the set of branched projective structure on X of divisor D this one is an analytic space. Okay. But we don't know much about this analytic space. So we don't know if it is empty or not. We don't know if it's smooth. And another result is from is more about so this is about the Teichmuller map. The other one is about the holonomy map. It's by Calzamiglia, De Roy, and Francaviglia. 2014. They say that if we take a representation in the nice complex manifold R0 of S, and we look at the fiber of the holonomy map above the class of rho, then it is a complex manifold of dimension n. But again, they don't say how these complex manifolds behave with respect to each other, and also remark that in the branched case, it is not like in the unbranched case. The holonomy can be anything. You take any flat CP1 bundle over a Riemann surface, it has a non-flat section. So the holonomy map does not take values in R0 of S. Not only in R0 of S. And so the result I want to present, it was published this year. And again, so it is an analog of this one. So the first point is that Pn of S, it is not anymore a complex manifold, it is an analytic space. So it has singularities. And the singularities can be characterized in terms of the monodromy, of the holonomy. So if I take P in Pn of S, P is singular. So if and only if I write rho its holonomy, the holonomy, so rho verifies a condition star. The condition is that its image, the image of the representation rho inside PSL2C, is commutative. It's an abelian subgroup of PSL2C, and it fixes a point in CP1. So I won't give an analog of the second point here. I will talk about it a bit later. And the analog of the third point, so I didn't say an analytic space of dimension 6G minus 6 plus n. So the third point is that in restriction to the pre-image of R0 of S by the holonomy map, the holonomy map is a holomorphic submersion. Okay, so of course it cannot be a local biholomorphism for dimension reasons, but it is still of maximal rank for any wherever it makes sense. So just a remark, the condition star about the representation rho, it can be said also that up to conjugation, the image of rho is contains only translations. Or it contains only dilations. And this condition is also the condition for rho to be a smooth point of the representations of the space of representations. So not without quotienting by PSL2C. So from by one of S, PSL2C. Okay. So this is the result I wanted to present. And now I'm going to talk a bit about the proof. So first I will explain the story. So I will explain how we see that Pn of S is an analytic space. This is the main point of the of the proof. So in the unbranched case, I will explain the classical story. So it is the analytic structure is given by the Schwarzian parametrization. So I fix a complex structure, and I take two projective structures on X. So in the fiber of type 0 above X. And the P1 is given by an atlas UI Fi, and P2 by an atlas UI Hi. Then on the open subsets UI, I can define the difference P2 minus P1 as the Schwarzian derivative of the map Hi of the holomorphic map Hi in the charts Fi times dFi square. So this bracket is the Schwarzian derivative. So if I write hi is phi of fi, then the brackets hi fi, it is 5 seconds over phi prime minus 1/2 5 seconds over phi prime squared. The Schwarzian derivative. And so these are local quadratic differentials that coincide on the intersections, ui intersected uj, which is a property of the Schwarzian derivative. So that's globally P2 minus P1 is a global holomorphic quadratic differential. And the space of quadratic differential always has the same dimension. It doesn't depend on x, 3g minus 3. And so, in fact, these affine space glue well together so that P0 of S over T of S is an affine bundle. And the dimension is the dimension of T of S plus the dimension of the fiber, so 6g minus 6. So that is the story in the unbranched case. Now, in the branched case, we still have a Schwarzian parametrization, and in fact, if we fix only the complex structure and we look at the fibers of Teich n, the Schwarzian parametrization does not give much. In order to get something, we have to fix, like Mandelbaum did, we have to fix x and an effective divisor on x and look at the structures of divisor D. And then what we get through the Schwarzian parametrization is an analytic space of branch projective structures. So we don't know much about this analytic space, and it doesn't deform well when we vary x and D. So the key ingredient in the proof is the notion of branching classes. So this can be seen as infinitesimal branched projective structures at the branch points. So again, x is in T of S. I will fix also a point in the Riemann surface x, and I will fix an integer n. And the space I'm interested in, I write it Cxn, it is the space of germs of ramified coverings from a neighborhood of little x to a neighborhood of 0 in C. So F is a ramified covering of degree n, so an n plus 1 sheeted germ of n plus 1 sheeted ramified covering. So there is on Cxn, there is an action of the automorphism group of C at 0. It acts on Cxn by postcomposition. And the point is that the action is not transitive. So if n equals 0, it is transitive, but if n is at least 1, it is not transitive. And this can be seen easily because so a neighborhood of little x, it can be seen as the disjoint union of the fibers of F. And such a partition, it is invariant if we compose by bijection, if we post-compose by bijection. So this action is not transitive, and thus there is a space of orbits that appears. So it's an infinite dimensional space, and me, I want a finite dimensional space, so I will take not germs of ramified coverings, but jets of ramified coverings. And the right order to take is 2 times n plus 1 for technical reasons. Where F is in Cxn. And so the branching classes are the orbits of the action of the automorphism group of C at 0 on Cxn tilde. So now if I take a divisor, D is the sum of Ni xi, effective divisor on X. The branching classes on X of divisor D is so the tuple where I take one branching class, one orbit at each point of the divisor. So say I goes from 1 to R. And this is what I call the space of branching classes. On XD. So the important fact about branching is, so if I take P, a branch projective structure in the fiber of type n over X, such that the P is has branching divisor D. Then I can consider a branching class associated to P, that I write alpha of P. Simply by taking the jets of the charts of P at the points of the divisor. And the important fact is that if I take A in AXD, the the fiber of alpha above A, so the space of branch projective structure of branching class A, this one, maybe it can be empty, but if it's not empty, it is an affine space directed by the global quadratic differentials that vanish on D. So we get the same situation as in the unbranched case. So, okay. So in order to have an affine space of branched projective structure, it is not enough to fix the complex structure. It is not enough to fix the divisor either. You have to fix something more that is a branching class. How much time do I have? 3 minutes. 3 minutes, okay. So, okay, so maybe I stop here. So, yes, because then the story is more or less the same as in the unbranched case. Now that we have affine spaces of branch projective structures.
Do you have any question?
So is the submersion part of your statement a consequence of the result of Casamiglia, de Rouen, and Francamiglia, or?
No, you can see it directly without using. I find back their results. Like
okay, it's more in that direction. Okay.
Yes, yes. It's really similar to the method that. To the proof of Hubbard that the space of projective structure is biholomorphic, is locally biholomorphic to the space of representations, the character variety. So more or less the same proof.
Nice. Thank you.
Any other question?
Yeah, yes, thank you. So on Riemann surfaces, the projective structures, classical projective structures, generalize to opers. What about the branched ones? Do they also generalize to something?
So you can also have a you also have a notion of oper that is so something like f xp fs, where p it is a CPN bundle. And X, so this is a PSL NC oper. And X is still a curve. But P is a CPN bundle, and S is a transverse to the foliation, but not only transverse, it's like something, it's very transverse. It's the n-jet of S is not contained in a hyperplane of CPN. So there is a, and so you can define a branched oper, like something like that, where S is only generically transverse to F, and this is also a notion. Yeah.
Any other question? So we thank Gustave again.
Thank you.